Thanks for the warm welcome, Shraddha. Hope all of you are doing great. I'm sure many of you would have tried your hands on generics when it launched last year in Go. Today, I plan to talk about it from a language design perspective. My name is Mohit. I work as a software engineer at One2N, and I love to explore the internals of programming languages and to get the nitty-gritties of it. And when I'm not doing that, which is most of the time, I love brewing coffee and talking about it. And then I'm constantly planning road trips, even though I'm not sure when that's going to happen. And then exploring food joints. So people who are visiting Pune just for this conference, please hit me up. I'll suggest you some places. So let's start our talk. Before we ask what is generics, let us see why do we even need this. Okay, so you write this function sort integers. Forget that there's a sort package in Golang right now. You pass it an array of integers, and then you sort it and return the sorted ones. It's not an in-place sorting. The next day, you need to sort floating point numbers. So you write this function. Same, you pass an array of floating point numbers, sort it, return it. The next day, business comes up to you with a requirement that we need a custom type called amount. Now this amount is monetary amount in your system, and that needs to be sorted as well. So do you see the problem over here? We are writing the same logic again and again, just for different types. And apart from the very violation of the drive principle, the bigger problem here is maintaining this code. So if you want to change one line of logic in your sorting, you need to make the changes everywhere. So how did we solve this before generics? Any guesses? Just keep in your mind and let me know if you thought about the same thing. Used reflection. A show of hands who have used reflection before on production. Okay. Let's talk about reflection now. So if you treat your source code as just code, you can run it on a CPU, right? But if you treat your source code as data, you can introspect it. You can even update it during runtime. Just like you can do for your program data. And this is known as metaprogramming, of which reflection is a part. So reflection allows you to get into the details. You can examine your structure of the program during runtime. And before I show you an example of reflection, now let's discuss about two things: how interfaces are implemented in Go, and what is the concept of empty interface. So consider interface values to be composed of two things. One is the actual value that it holds. The other one would be the type metadata of the concrete type. And an empty interface is an interface which has zero methods. What that means is that an empty interface variable would be able to hold any type. Okay, keep that in mind, because that will come in handy later. Cool. Now we want to build a basic ORM tool, okay, which just generates SQL queries for you, an insertion one. So you pass this order structure. It creates a insert into order with the values that you've passed. Now you can even pass different structures, and it should create the queries accordingly. So how do we solve this? Okay, so this is a create query function which takes an empty interface variable. Okay, that means it can take any type. We create an order and then pass it to create query. Okay, I want to highlight three key things over here, which are value of, type of, and kind. So when you pass the order structure, the value of that variable would be this whole thing. The type would be order, because this is a custom type that you created. And the kind would be struct, So there's the usual confusion that what's the difference between type and kind. So type is the usual type of a variable that you have defined, whereas the kind would be the underlying type, or the native type, which is in this case is a structure. Okay? Let me quickly walk through this program. So you do you check if the kind is a structure. In that case, you get the name. You start preparing the query. Here we are iterating over the individual fields of the structure. Now we do a switch case on it. In case it's an integer, you process it like this. If it's a string, do it this way. Otherwise, throw an unsupported type. So let me run it for you. For the order, it created this one. For the employee, it created this query. And since we passed an integer over here, it threw an unsupported type. I hope this is clear. I'll move back to the slides. Okay. Now you may be wondering, if reflection solves the problem, why do we need generics then? Right? Well, reflection comes with its own sort of problems. Rob Pike said that clear is better than clever, and reflection is never clear. You just saw the program, how awkward it looked like. Instead of focusing on the business logic, we were focusing on handling types. We were focusing on handling edge cases, exploring the items of the structure instead of acting on them. This is why reflection is not used so much. Another case is that reflection does not provide you compile time safety. The earlier you receive the bug, the earlier you find your bug in the software's life cycle, the better it is for you. If you want to know more about why dynamic is dangerous, I've linked a good article. I will reference it at the end. Also, since reflection is doing your compiler's job at runtime, it will lead to a performance overhead. So let's talk about generics. What is generics? It's a way of writing code that does not distinguish between different types. It helps you to write interoperable and adaptable code. Don't bother about this syntax for now, we'll get to it. If you break down generics, you'll get these three concepts. And if you are able to understand it, you've grasped the whole thing. So these three things are type parameters, introduction of type sets and how the interface syntax was extended to include these, and then type inferences. Let's talk a bit about this in more detail. Okay, let's start with type parameter list. So this looks very similar to a function parameter list, right? Instead of being enclosed in parentheses, this is enclosed in square brackets. Let me give you an example. So this is a normal non-generic min function. It takes in two floating point numbers, finds the minimum, and returns that. How do you make it generic? How do you parameterize it? This way. So now instead of x and y being float type, you make it a custom type called t. Now you need to define t somewhere, right? That's where you use the type parameter list. And t is something called constraints.ordered. I'll explain it eventually. So how do you call this function now? You need to tell the compiler what my type argument is going to be. So you need to tell the compiler explicitly that 2 and 3 are integers. Hence you use this syntax, this gmin with the type argument. Now this process is known as instantiation, and it involves two steps. So first step is that all the t's in your program are going to be replaced by int. The second step is that the compiler would check whether int satisfies that constraint or not. If it does, all happy and good. Your program will compile successfully. Otherwise, it will throw out an error. So that's the beauty of using generics. You'll get the feedback during compile time, and you won't have to wait until the runtime. And the cool trick I'll show is that you can use this type instantiation, assign it to a variable. And now this fmin becomes a non-generic function. You can use it directly with floating point numbers without any type arguments. Let's talk about type sets now. So what are the values that you can pass to this x and y? It could be any floating point number that can be represented in 64 bits, right? Similarly, what are the values that can be passed to t? So t could be any type whose values can be ordered, or they can be compared by less than or greater than operator. If you say that type of x and y is t, then type of t in this case would be constraints.ordered. So now it's another level of inception. So we can call constraints.order as a meta type, a group of a collection of types. Now let's see what this constraints.ordered means. So constraints package was introduced in Go 118, and ordered is an interface inside that. Okay? This interface embeds other interfaces, integer, float, and then has a native type string. Then integer also embeds signed, unsigned, and then finally signed would have the native types. You may be wondering how this syntax came to be. How the hell there are no methods? How are types being embedded directly? What are these pipe symbol? What is this tilde symbol here? To give you an idea about it, let me explain this. So consider this picture. An interface is essentially a set of methods, right? And any type that implements all those methods can be said to be the implementer of that interface. Okay? There's another view to this. That is this one. So if you take all those types that implement this interface, put it in a box, make a set out of it, okay? Now can't we say that this interface defines this type set? And what this view essentially helps you with is to explicitly add types. So now P and R were already there. I can explicitly add another type into it and say that this one implements that interface. What this helped us with is to do this. We are explicitly adding types into this set, which is interface. So this interface is satisfied by int, string, or float 64. That's what this pipe symbol means, a union of types. And the tilde symbol means all the types whose underlying type is string. If you consider this user category, this is an alias of string. And since we have used a tilde symbol above it, over here, user category also satisfies this interface. Let's talk about type inference now. So, as I said, if you want to call the gmin function, you would need to pass the type argument, integer. But the compiler already knows that A and B are of type int using this line. It already knows that. If that's the case, then we can go ahead and omit the type argument, use the generic function directly. There's another inference called constraint type inference. Due to lack of time, I won't be able to get into the depths of it, but feel free to reach out to me after the talk if you want to know more about this. I'll give you a gist of it. So what it does is, let's say you have a type parameter list which has multiple parameters, and those are interdependent on each other. So if the compiler is able to understand the type of even one type, it will be able to gauge the types for the other ones as well. I'll urge you to explore other inferences as well, which were introduced recently in Go 121. Let's head back to the slides. Okay. Now, since we've talked about how generics can be broken down into these concepts, I'll also want to explain how generics is being implemented in other languages. So there are two key ways to implement generics. One is boxing, not this one, but this one. So what it means is, you take all the types that your generic function will operate on, and then make it act and look the same. So how do you do it? You take those types, allocate it on heap, take their pointer and pass it to the function. And since pointers look all the same to the function, all you need now is the location of the methods that you need to operate on. How do you get those methods? So in boxing, we usually pass a virtual method table. And that contains all the function pointers to your methods for all the types. Another way to do generics is monomorphization. I know it sounds scary, but it isn't so. So what we do is we start with a generic function, and the compiler will see that the program has int and float 64 types that are using this function. So it will create two separate copies. So two native functions for that. Okay? That's it. That's monomorphization. While boxing would lead to a smaller amount of generated code, a smaller compile time, but that would also lead to a huge runtime overhead. On the other hand, this will lead to a larger compile time. And since you are creating multiple copies, a larger binary as well. But then, this is the only sort of parametric polymorphism that has zero runtime overhead. Okay. Now the next natural question would be, how is generics being implemented in Go? So Go kind of went midway between these two paradigms. It chose partial monomorphization, which they call GC shape stenciling with dictionaries. I don't know why. So GC shape is a term very specific to Go. So it talks about how it looks like in the memory, how the types look like in the memory. Now, two types can be said to be of same GC shape if and only if their underlying types are same, or if they are of pointer types. Okay? And in that case, compiler would create two copies. If the GC shape is different, it will create separate copies for them. Otherwise, if the shape is same, it will use the same function. So to create a balance between the amount of generated code and the runtime performance. Okay. So you may be wondering why different copies for different shapes. Let me give you an example. Consider summation of integers versus summation of floating point numbers. Integers would use integer arithmetic. On the other hand, floating point numbers would use floating point arithmetic. Hence, two copies. But in case you pass a pointer to your generic function, the compiler will think that all the pointers are same. And for that, it creates just one function. In that case, you need, again, the same boxing concept comes over here. You need to tell the compiler, or the runtime rather, where the methods live. And that's what the dictionary is used for. It actually comes with the info of the method pointers for all the type parameters. It is passed as the first parameter to your function. Okay. Another way to look at it is, think that all the pointers, whether it be a time pointer or a string builder or a byte buffer, or even your custom struct pointer, all look like the same to your compiler. So you need to tell where the methods reside for them. That is what this dictionary is used for. I want to talk about the performance implication of the way generics was implemented in Go. So this is a benchmark for write function call on IO byte writer. Okay. The first one is the monomorphized. Obviously, that's going to be the fastest because that's just native function call. Second would be interface. This is how generics was being done earlier, before generics was introduced in Go 18. So if you have an interface and you want to call a method on it, it involves one level of indirection. How? You remember I told you that interfaces contain the value and the type metadata? So that type metadata is known as itab. And that itab actually holds the function pointers, along with a host of other things. So in case you want to call a method on interface, you dereference that itab, get the function pointer, and then call it. Okay? Hence, it's slower than monomorphized version. If you have a generic function and you pass a pointer to it, In that case, what happens is it involves two levels of indirection. First, you need to dereference the dictionary. Get your type parameters itab, and then dereference that as well to get the function pointer for that type. This way, it's slower than the interface. God bless you if you start using, passing interfaces as type arguments. In that case, what happens is, apart from involving two levels of indirection, there's another method call that happens internally, an assertion on interface, which leads to this kind of performance. So I would urge you to avoid passing interfaces as a type argument. Looking at these benchmarks, don't think that you should totally avoid using pointers with generics, or even avoid using interfaces as type arguments. That's not a gospel. Totally depends on your requirement. Most of the time what happens is it's your business logic that takes the most of the runtime, instead of the runtime doing its own thing. If you feel like your function is performing slow, look into your logic first. And then you can think about improving the runtime performance. Okay, let's wrap our talk by discussing when to use generics. So I would recommend you to, when you start writing your program, don't start with designing types or constraints or interfaces. Start writing your business logic, and then when you require them, use it. Another key place where you can use generics is functions that work on composite types, like slices, maps, or channels, that don't assume the underlying type of that, of the element type. So I'll give you an example. Let's say you have a map and you want to return all the keys. So does it matter what the key type is? No. In that case, you can use a generic function. This is one function that I wrote a couple of weeks ago. So I wanted to find the intersection between two slices. Now, here also it doesn't matter what kind of slice it is. Whether it be a string slice or an integer slice, just give me the intersection. So this is what the skeleton would look like for that. Another great place to use generics is general purpose data structure. So things like binary tree or hash set or linked list, you can use those. You can use generics at those places. So in this example, tree takes an empty interface, so you can pass any type to it. What benefits it has is that at the compile time, before that, look at this string tree. At the compile time, you are able to tell the program that I'm going to use a string type of tree. So internally, the program is not going to store your values as an interface, again, which will lead to dereferences. It will store it natively as string. So that has also a performance improvement. And the common thing is that if all the methods look kind of same to you, just the type is changing, that can be a good place to use generics. Now, more important than when to use generics is when not to use generics. So consider this example. You want to call the read function on an IO reader. Use the first approach instead of the second one. Why? Because the first approach is easier to read and write. And there's no performance improvement in using the second version here. So go ahead with the first one. If you have different implementation of a common method, then you can't use generics over there. For example, reading from a random number generator would be very different from reading from a network or a file. So use an interface over there. Create a read method and implement it for different types. And if you have different implementation for a common method, and you don't want to implement it for all the types. Example is, in the encoding JSON package, you have a Marshall JSON function, okay? So now look at this way. Marshalling an integer would be very different from marshalling a structure, right? And you also don't want to create the Marshall, implement the Marshall JSON function for every custom type that you are going to create. In that case, use reflection. That's what this library uses. So at runtime, it's able to gauge the underlying types and then marshal it accordingly. If you ask me to give you a one thumb rule, or if you want just one takeaway from this talk, is to use generics to avoid boilerplate code. When you see that methods are being repeated with same logic, just for different types, you can think of using generics over there. Corollary, you should not start using this prematurely. Wait until you are about to write the boilerplate code. These are the references for my talk. I would highly recommend to go through these, especially the second one. It's a very detailed article on the internal workings of generics. I will post this on my Twitter and LinkedIn as well. I'm open to questions now. And we also solved some really challenging problems in our Go bootcamp, so feel free to check it. Yeah.
So I wanted to know a few more things. You, in the previous slide, it was written that generics are not that optimized, but as I'm subscribed to Golang issues, they have been working on optimizing it, and it will be released in a current version.
Yep. So see, generics was just launched last year.
Yeah, just last year.
And the first implementation or the first cut that they made, they went to go with this design approach, the midway. So monomorphization was the practice in system level of languages, C++, D, Rust. So those provide performance benefits during runtime. The trade-off would be the compile time. Go wanted to create a balance between those. Okay. And obviously, as we go forward and we get the feedback from the community, the Go team would eventually, improve things over there.
And I also wanted to ask one thing that in your second last slide, you said that you use reflections when can you?
Yeah, sure. So you should use reflection in the case when you have different implementations for a common method, and then you don't want to implement all those methods for all the types.
But I think you can you can define your own constant for the types you want, then and you can typecast it to the empty interface. You can also do it like that.
But how many constants are you going to create? And how many types? Can you ascertain the types that are going to come in the future? That's the problem. And if you definitely use reflection.
I mean, okay. Got it. Thank you.
Because we cannot ascertain the number of types that are going to come in the future and keep on adding to the same constraint. Yeah, definitely you can create new constraints tomorrow for those types. But when you create a standard library, you don't design it in a way that it's going to change very frequently. So the best approach here would be to go with reflection.
Okay, thank you.
Any other questions? Yeah.
So point number 3, we have already seen using reflection.
Yes.
How far are we to actually implement or provide the feature of method overloading? When it comes, because we are already there. We are at the door when we are already providing monomorphism.
Yes.
So we are just like a step away from giving method overloading there.
Yep.
Why don't we do that? What is stopping us from doing that?
This I haven't looked into, but yeah, great question. I can definitely look into this and we can connect later. Yeah.
Okay, thank you so much, Mohit. And in fact, thank you to all the speakers for giving solutions to our